All right. So today we are going to cover section 3.3. The focus of today's class is to find zeros for polynomial functions. If the polynomial functions are degree 1 or degree 2, then we can use the method of solving equations to find the solutions. For example, if you have a degree 1 polynomial function, f of x equals 3x plus 4, how do you find the zero? And you make f of x equals 0, right? Make 3x plus 4 equals 0, and then solve the equation for x. That's how you find the zero for a polynomial if the degree is 1. If the degree is 2, similarly, let's say we have x squared minus 2x plus 3, right? And then you make f of x equals 0, and you solve this quadratic equation using the methods we have learned. You can use the famous quadratic formula to find the two zeros, right? But if the degree of the polynomial function is 3 or 4 or higher, and the factoring those polynomials are difficult or impossible, then we need other methods to figure out the zeros of those polynomial functions. So that's what we need to focus today. We have a theorem that could help us to find the zeros of a polynomial function. The name of the theorem is called the rational zero theorem. As the name shows, this theorem helps us to find the potential rational zeros for a polynomial function. Means the zeros we found is possible to be an actual zero, but it might not really is, but it's potentially could be the zero. And also those zeros have to be rational. This theorem does not help us if the polynomial function has an irrational zero or non-real complex zero, like a plus bi. All right, so this is the theorem. The theorem applies when the polynomial function have coefficients are integers. So it has its limitation for the application. And what does this theorem say? We have a polynomial function. Let's say we use f of x. We use this polynomial function as an example to explain what does this theorem talking about. Let's say we have a polynomial function f of x equals 35x cubed minus 92x squared plus 47x minus 6. This polynomial function is a degree 3, right? The function is a polynomial function. The degree of the polynomial function is 3. And the rational zero theorem could help us to find all the potential rational zeros for this polynomial function. And the key thing is the last term. The last term is a constant and the leading coefficient. The leading term has x in it, right? So we do not worry about variable x. We look at the coefficient of the leading term. So rational number, the definition for rational number, simply put, you can see rational number as any number that can be written as a fraction. The formal definition for a rational number is any number that can be written as the quotient of two integers. So this is an integer. This is also an integer. And the integer on the denominator cannot be 0. Denominator cannot be 0 is a common sense in algebra. Any number that can be written as a quotient of two integers is a rational number. Simply put, you can understand any number that can be written as a fraction as a rational number. So we are looking for rational zeros for the polynomial, all the potential, all the possible zeros for this polynomial. And here we have a question. What is zero? What is zero? Suppose, okay, suppose we have, I'm just made it up. This might not be the potential zero. Suppose we find out the 1/2, which is a rational number as a fraction, is a zero of f of x. What does that mean? When we say a rational number is a zero of the polynomial function, what does that mean? It means if we plug in x equals 1/2, we got a zero. Zero of a polynomial function is a value that will make the function be zero. Does that make sense? You can also understand zeros as the x coordinates of the x-intercepts of the polynomial function. All right, so of course here we only can find rational. Irrational, this theorem doesn't help. So how it works, what you need to remember is this one. Is the formula for finding the potential rational zeros. P over Q represents the potential, represent a potential rational zero. P over Q. PQ are both integers. P in the numerator. P is a factor of the constant term, the last term. Q is in the denominator. Q is a factor of the leading coefficient. I said here a factor of the first term, but we really do not include the verb x in it, only concern the coefficient. And in this case, in this problem, the constant term is -6. The leading coefficient is 35. And we can find all the factors for the last term, -6, and then put it on the numerator. And then we do not have to worry about the sign. We always start with plus minus, and then put the absolute value of those potential rational zeros in the braces. So do not consider the sign. Just think about the absolute value. The absolute value of the last term is 6. Can we find all the factors for 6? 1, right? 1 is a factor of 6. 2 is a factor of 6. 3 is a factor of 6. 6 itself is also a factor of 6, right? So the last term is -6. Do not worry about the sign. Only take the absolute value, which is 6, and then find all the factors of 6 and then put them above the bar. 6 has 4 different factors, 1, 2, 3, 6, and just put them here like that. And the denominator is Q. Denominator of the potential rational zero is Q. Q is a factor of the leading coefficient. In this case, leading coefficient is 35. Let's find all the factors for 35. 1 is a factor. 2 is not. 3 is not. 4 is not. 5, yes. 6 is not. 7, yes. Even numbers are not factors of 35 because 35 is not even number. 9 doesn't work. 10, no. 11, no. 12, 13, 14, 15, 16, 17, 18, 19, 20. And you can see those doesn't work, right? And what's the next one? 35. 35 has 4 different factors. 1, 5, 7, and 35. All right? So this is how do I take notes, apply the theorem. I write P over Q equals and plus minus, and then put a braces. In the braces, I have a fraction bar. Above the fraction bar, I have all the factors of the absolute value of the constant term in the polynomial. And the denominator on the below the fraction bar, I have all the factors of the leading coefficient. And how do we understand this notation? So PQ could be, P over Q could be 1 over 1, right? 1 over 1 is 1. And remember, we have plus minus in front of that, so -1, also a potential rational zero. And then we can do 1 over 5, right? Like here, 1 over 5. Or -1 over 5. Or 1 over 7, or -1 over 7, 1 over 35, -1 over 35, or 2 over 1, right? -2 over 1, or 3 over 1, or -3 over 1, 6 over 1, or -6 over 1, or 3 over 5, or -3 over 5, or 3 over 7, -3 over 7, 6 over 5, -6 over 5, 6 over 7, -6 over 7, 6 over 35, -6 over 35. Do you see what happened? Do you see what happened? The numerator of the potential rational zero must be a factor of the constant term in the polynomial. The denominator of the potential rational zero has to be a factor of the leading coefficient. I need a response. Do you see what I'm talking about so far?
Yeah, I understand it.
Thank you, Haida. Then let's go over the options here. According to the rational roots theorem, rational roots theorem or rational zero theorem is same thing, okay? Same thing. Which of the following does not represent a possible pair of rational roots of the polynomial? How about we determine which one is the potential, and then the rest of them is the one they are not possible rational roots, okay? It's the pair of, because it has plus minus. To the first pair, 6 over 1. It is, right? It is. Because 6 is a factor of the last term. 1 is a factor of the leading coefficient. As you can see, I have 6 on the top, I have a 1 on the bottom, right? The second pair, 2 over 7. Well, that one is as well. Do you see I have 2 in the numerator above the bar? I have 7 below the bar. And the third pair, 3 over 2. 3 over 2 is not. Do you guys see it? Ether, do you see it? 3 over 2 is not. Hello? 3 over 2 is not a potential rational zero of this polynomial function, right?
Yeah, no 3 over 2.
Because 3 is fine. 3 is a factor for the numerator, but 2 is not a factor of the denominator, right?
Yes.
Yeah, so this one is not. What about 3 over 7? Do you see 3 on the top? Yeah, 3 over 7 is. What about 3 over 1? It's 3, but it's 3 over 1.
Yes. Yes.
Yes, very good. Very good. What about 3 over 35? Yes?
Yes.
3 on the top, 35 on the bottom. This one
Yes.
is potential pair of roots. And the 1 over 5, yes.
Yes.
2 over 5, yes. 6 over 35, yes. 6 here, 35 here, right? Very good. 1 over 7, yes. 1 appears on the top, 7 appears on the bottom. Okay, very good. So this is a multiple choice question. According to the rational roots theorem, which of the following does not represent? Yeah, okay, we only found the one pair. The rest, those I bubbled, they are potential roots. They're just potential, okay? In order to know if they are actual roots of the polynomial function, we have to do something else. We have to use a synthetic method to check one at a time. It's pretty time consuming, some of the problems. I hope this is clear. Yeah, the key, the important thing for number 12 is you understand the content of this theorem. You know when to apply the theorem, and you know how to apply the theorem. Important thing is you mark the constant term and then the leading coefficient, and you do what I do here. Let me highlight. You do what I do here. P over Q equals plus minus, and draw a big braces, and draw a fraction bar. On top of the bar, you write all the factors for the absolute value of the last term. And on the bottom, you write all the factors of the leading coefficient. And then you can find a lot of, for this case, a lot of potential rational zeros, right? Okay, so that is number 12, the content of the rational zero theorem. And next topic, find all zeros of the following polynomial functions. A fact here we need to understand and remember, the complex number set. In the complex number set, the number of zeros of a polynomial function is the same with the degree of the polynomial function. In other words, if the polynomial function has degree n, then in the complex number set, the polynomial has n zeros. Those n zeros could be real numbers, could also be non-real complex numbers. This actually is a very important theorem. This actually is a very important theorem. I think it's called the fundamental theorem of algebra. In the complex number set, the number of zeros of a polynomial is the same with the degree of the polynomial. Let me get a space here. The first polynomial we have has a degree 3. X cubed plus x squared plus 9x plus 9. Here we need to find all the zeros, right? Find all zeros of the following polynomial function. Since the polynomial has degree 3, we need to find all three zeros in the complex number set. And this polynomial is kind of special. The reason I say it is special because it is easy to factor. It is easy to factor. So let me factor this polynomial for you. This polynomial has 4 terms. In foundation 2, you might remember, if we need to factor a polynomial containing 4 terms, we should consider a method is called factoring by grouping. And this one actually, grouping method applies to factor it. We can group the first 2 terms together and group the last 2 terms together. And then factor the GCF from the 2 terms in the first group. X cubed plus x squared. The GCF is x squared. Factor out x squared. And in the parentheses, we have x plus 1. And 9x plus 9, those 2 terms in the parentheses, they have GCF 9. We can factor 9 out. Factor 9 out. Then in the parentheses, we have x plus 1 as well. And as you can see, those 2 groups, this part and this part, they have a common binomial factor. In the parentheses, x plus 1, in the parentheses, x plus 1. So we can factor that part out. Factor x plus 1 out. From the first part, we have x squared left. From the second part, we have 9 left. All right. So x plus 1, as you can see, if we write plus 1 in red, and we know the opposite of the red number, -1, is a 0, right? Because if you plug in x equals -1, the first parenthesis becomes 0. Then the value of the polynomial function is 0. So we found a 1, 0 already, which is -1. Is the opposite of this number in red. And then you know we have 3. We need to find a 3, all 3, because degree is 3, right? Now we only have a 1. What about the other 2? What about the other 2? So in order to find the other 2 zeros for the polynomial function, we can try to make this part, this binomial, as a 0. If we make x squared plus 9 equals 0, and we isolate x squared on the left side, we have x squared equals -9. If we are finding the zeros in real number set, and we are done, because the polynomial function only has one real 0. But we are looking for all the zeros, all the 3 zeros in a complex number set. So we need to go further, okay? We can solve x squared equals -9. We apply the square root property. We have x equals plus minus root -9. Do you guys remember how do we process a square root of a negative number? When you see a square root of a negative number, you rewrite it as a square root of the positive number I, right? In terms of I right away. Square root of -9 is square root of 9i times I. I hope you remember this. And x equals plus minus 3 plus minus 3i. Plus minus 3i. We found another 2 zeros. Guys, we found another 2 zeros. The other 2 zeros, they are not real numbers. They are non-real complex. 3i, -3i. So some of you, if you can actually see here, x plus 1, x squared plus 9 actually can be written as x plus 3i times x minus 3i. If you can see it, if you don't see it, it's fine, totally fine. And so if we write these numbers as red, those are 3 red numbers, their opposites are the 3 zeros. -1 here, -3i here, positive 3i here. Those are the 3 zeros. Is that clear, everybody? Sometimes factoring works. This case is the case that we can apply factorization to find the zeros. Can you give me some feedback?
I get it.
Okay, thank you. And in fact, this is a very important conclusion. You need to remember, okay? In fact, if a polynomial function has a non-real complex root, then the conjugate of that root is also a root. What I'm trying to say is, let's say here is a polynomial function. Let's say P of x is a polynomial function. If a plus bi is a 0, then a minus bi is also a 0. If the polynomial function has a non-real complex 0, then it must have a pair of non-real complex zeros. And the pair of complex numbers, they are conjugate. All right? Yeah, if a plus bi is a zero of p of x, then a minus bi, the conjugate of a plus bi, is also a zero. So that's good. That means if we know one non-real complex zero, we can get another one, right? We know two of them. If we know one, we actually know two of them. Okay, let me go over the two important conclusions before we keep going to we move on to the next problem. The first conclusion is actually a very important theorem. I think it's a fundamental theorem of algebra. A polynomial function has n zeros if the degree of the polynomial function is n. In other words, how do we know how many zeros a polynomial function has? We look at the degree of the polynomial function. If the degree of the polynomial function has 4, then we know the polynomial function has 4 solutions, four roots. If the degree of the polynomial is 10, then we know it has 10 zeros. And knowing we are talking about finding zeros in a complex number set. So the polynomial has 10 zeros in a complex number set. If the degree of the polynomial is 35, then the polynomial has 35 zeros in a complex number set. All right, so this one has 3 because the degree is 3. Let's move to the next problem. This polynomial f of x equals 4x cubed plus 16x squared plus 23x plus 11. This polynomial has degree 3. Let me restate our goal, our task here. We are finding all the zeros or roots, whatever you want to call it, is the same thing, in the complex number set. Since the degree of the polynomial is 3, the polynomial has 3 zeros in the complex number set. Now we need to find all the 3 zeros. Again, 0 is a value. When you're plugging in the value, when you replace the value, replace variable x with the value, you have 0 as the output. Do you guys remember functions like a machine? You still remember the function is a machine, right? And the machine produces exactly one output whenever you give the machine an input. So zeros are the inputs of the machine that could give output equals 0 at number 0 as output. So those are the zeros. All right, let's see this. Let's observe this polynomial. Factorization seems difficult. Yeah, we don't really see the pattern that we can apply the grouping method. So we are going to do the theorem we learned the beginning of today. We are going to apply the what is that called? Rational roots or zeros theorem. All right. So we're gonna write P over Q. Yeah. So firstly, let's find some rational roots. Okay. Firstly, let's find some rational zeros. Rational number set is a subset of complex number set. Yeah, we do one at a time, right? Let's consider the potential rational zeros first. P over Q equals plus minus. This is what I do. I hope you do the same thing. Numerator, we're gonna have all the factors of the constant term. 11 is a prime, so only 2 factors, 1 and itself. And the denominator are all the factors of the leading coefficient, which is 4. 4 has factor 1, 2, and itself, right? So let's see. We have all potential or possible POS. Rational zeros are plus minus 1, plus minus half, plus minus 1/4, plus minus 11, plus minus 11/2, plus minus 11/4. And those are all the possible rational zeros of the polynomial function. This is a lot, by the way. Okay, 1/1, 1/2, 1/4, 11/1, 11/2, 11/4, 1, 2, 3, 4, 5, 6, double 6, 12. We have 12 potential rational zeros. And we need to find, we need to go through those potential zeros and then find the actual zeros, the actual input that would lead to a 0 as the output. And how do we do that? We use the synthetic method. Synthetic. Synthetic method is what we learned that's the class before the spring break. So firstly, you need to make sure the polynomial function is in the standard form. Very, very important. Let's look at the polynomial degree 3, 2, 1, 0. Okay, it is in the standard form. And then we take the coefficients of the terms in the standard form of the polynomial. We have 4, we have 16, we have 23, we have 11, right? And we're gonna try all the 1, 2, 3, 4, 5, 6, all the 12 possible rational zeros. Sometimes we get lucky. The first couple times we can find it. Sometimes we have to really, if you are not lucky, have to spend a lot of time to figure out which one is, right? Okay, let's try 1. I will try 1 first. And then bring this down. 4 times 1 is 4. 16 plus 4 is 20. 20 times 1 is 20. 23, 20, 43. And you can see you are not going to have 0, okay? Yeah, let me continue. Let me finish though. 43 times 1, 43. 11 plus 43 is 54. That means what? That means f of 1 is 54. I also mentioned this last class, right? The remainder actually is the output of the polynomial function when the input is your k. When you're plugging in x equals 1, the output is the remainder. I mentioned this. Just watch the video, the recording from last class. So this also means 1 is not, okay? Yeah, let me put it here. 1 is not a 0. That one doesn't work, okay? That one doesn't work. Then you can erase those and then try -1. Let's try -1. Since the synthetic method is very fast method, even you have a lot to check. If you can get it done very fast, it's not too bad. So now we're going to do -1. Bring 4 down. -1, -4 here. 12. -12. And this one gives us 11. 23 minus 12 is, hold on. Yeah, 11. 11. And 1 times 11, 11. There we go. We got it. So the second try, we got an actual 0. Yeah, very important. So when the k is -1, the remainder is 0. That means f of -1 is 0. That means f of -1 is 0. Means the -1 is a 0. Yeah, you know the 0 actually making me a headache. Give me a headache sometimes. I think probably a root is a better name. If we think about, it's kind of confusing, number 0 and 0. Probably root is better name for that. So we found an actual root, -1. We found an actual root. -1 is an actual root, all right? Very good. We are making good progress. You know, should we continue? Because we have another 10 possible rational zeros. rational rules, I will not continue. The reason is because this polynomial has degree 3, and we already found a rational zero now. We can lower the degree by 1. Let me show you what I'm talking about, okay? So remember, how do we interpret the last row of the synthetic method? The last row of the synthetic method, very important. Let me highlight it in yellow. Remainder is 0. That means what? That means the polynomial function f of x has quotient. Let me write it down. Quotient. That means the quotient of the polynomial function when it divided by x plus 1 is 11. Look at the yellow. 11, go backwards, constant, and 12 times x, degree 1, and then 4x squared. Yeah, for the detail of the synthetic method, and look at the recording, watch the recording of last class. This is the quotient. Means what? Means if we divide f of x by x minus k, here k is -1, so x plus 1. When we divide f of x, the original given polynomial, by x plus 1, we have a quotient 4x squared plus 12x plus 11. That also means we can write f of x as x plus 1 times 4x squared plus 12x plus 11. You might wonder, where's the remainder? Remainder is 0. Do you see that? Remainder is 0. Remainder is 0. Since the remainder is 0, f of x, which is a dividend, equals divisor x plus 1 times the quotient. No remainder because it's 0. You see that? And the reason I said we do not need to check the other 10 potential rational zeros is because after this, after we apply after we found the quotient and write the original polynomial function as this factor is quadratic, and we have so many different methods to figure out the zeros for quadratic function, right? So this is quadratic, we can totally do it. We can totally do it. And now quadratic, I'm gonna use a different color. I hope I'm making sense, because this type of problem is very lengthy, very long. So I'm gonna do 4x squared plus 12x plus 11 here. Maybe you can factor it, right? Let me try a little bit. 2, 2, 11, 1, 22, or 1, 4, 11, 1, 11. No. Or if not, you know, the last resort, well, actually is a very important method is the quadratic formula, right? Let's do quadratic formula. A is 4, B is 12, C is 11. Delta B squared minus 4AC, B squared 12 squared minus 4AC. A is 4, C is 11, B is 12, 12 squared is 144, minus 4 times 4 is 16, 16 times 11, 176, and equals, I need to use a calculator to double check. The calculator. 144 minus 16, 4 times 16 times 11, and then minus, it's gonna be hold on, this is wrong. Oh my gosh, for sure this is wrong. It's gonna be negative 32. A 176 minus 144, 32. So negative 32. So delta is negative 32. So earlier we gave up trying to factor the quadratic trinomial, we made the right decision because it's not factorable. The polynomial function is going to have two non-real complex roots. So delta is -32. Let me know if I made some mistake by calculation. I have been sleep deprived since my baby girl was born, so sometimes I struggle with some simple thing. So delta is -32. Then by using the quadratic formula, x equals negative b plus minus big square root delta all over 2a. B is 12. The opposite of 12 is -12 plus minus square root of -32, right? And all over 2a. A is 4, 2a is 8. And then let's continue to simplify this expression. -12 on the top plus minus square root of a negative number. We see this again, right? Square root of a negative number is square root of the opposite, which is positive, n times I. Whenever you see square root of negative number, rewrite it as square root of the positive number and then times I. So square root of 32 times I over 8. And then let's simplify square root of 32. Square root of 32 can be separated as root 2 and then root 16. And what is root 16? It's 4, right? So 4 root 2. 4 root 2i. Can you erase that? Those details, those small parts, we have covered in the previous sections. Over 8. All right. So you guys remember my Mickey Mouse? Left ear, right ear, head. All the three parts have a common factor of 4. Only when the left ear, right ear, and the head, all the three parts have a common factor, and we can get rid of that common factor. In this case, the common factor is 4. So the left ear divided by 4, that is 3. Right ear divided by 4, root 2i. The head divided by 4, 2. Okay, there we go. That's the two non-real complex roots. All right, we got the 3. We got all the 3. The first one, we use the rational root theorem and the synthetic method. The first root we got is a rational number, which is a -1. -1 is the first root. The other two roots, they are non-real complex with I in it. Yeah, the first one is -3 over 2 plus root 2 over 2i. Yeah, I can rewrite this as -3 over 2 plus minus root 2 over 2i. And then the other one is a conjugate, -3 over 2 minus root 2 over 2i. If the polynomial function ever has non-real complex solution, non-real complex rule, then it's gonna have the complex rule as pairs, because the conjugate also is a 0, also is a root. We got all 3. It's pretty time consuming, right? How about let's summarize quickly. The task here is to find all the 3 roots for this polynomial function in the complex number set. In the complex number set, this polynomial function has 3 roots. How do we know that? Because the degree is 3. Whichever the degree equal to, that's how many roots the polynomial function has in the complex number set. And we start with, we did try to factor, but after we observe the coefficients, we don't think it works. So it does not work, factorization. The previous problem, yes, but that's kind of special. Since the factorization doesn't work, we apply the rational roots theorem, right? Yeah, we find all the 12 possible rational roots, and we tried a couple, and we got lucky. The second one we tried is an actual 0. How do we know? Because when we apply the synthetic method, the remainder is 0. The remainder is 0 means f of k equals 0 means k here is -1 is a root, All right. So that also means the original function can be written as x plus 1. This is also important. Can be written as x plus 1, which is x minus k. Your k is -1, so that's why we have x plus 1, okay? Your k is -1, so x minus k is x plus 1. X plus 1 times a quadratic trinomial. And how do we get that quadratic trinomial? That quadratic trinomial is the quotient of the original given polynomial. When we divide that polynomial by x minus k, we get x minus k here. And the yellow part can give us the quotient. That's how do we get a quotient. So synthetic method is very important application here. And then once we have the quadratic factor here, we have a lot of methods that can apply, right? We can try factorization, we can try quadratic formula. And we didn't make the right decision, give up the factorization because it's not factorable. And it turns out that quadratic trinomial has 2 non-real complex solutions. And those are the other 2 roots. So we got all the 3 roots. Please let me know, is that clear? It's a lengthy process.
Yeah, it's long, but I understand it.
Yeah, it's long, but okay, perfect. Appreciate your feedback. Let's keep practicing. And this one, I messed up the, okay, this one is fixed. Same requirement, right? The task here is to find all the, let's use roots. I think roots is better. Let's find all the roots for the polynomial function in the complex number set. Since the polynomial has degree 3, we are going to find the 3 roots for this polynomial function in the complex number set. All right, so that's the task. And then look at the polynomial. I don't think factorization gonna work, so we would have to use the rational roots theorem. Find all the potential rational roots for this polynomial p over q equals plus minus parentheses a fraction bar. The numerator is going to be the factors of the last term, and the denominator is going to be the factors of the leading term. So the last term is 2. I know it's -2, just ignore the negative sign. It's 2. So 2 has a factor. 2 is actually a prime number, 1, 2. And the denominator factor of leading coefficient. Anybody can tell me what's the leading coefficient? What's the leading coefficient of the problem, of the polynomial?
1.
Yeah, thank you. It's 1. Very good. It's good, right? We don't have a lot of numbers. Okay, the potential rational roots for this polynomial function are plus minus 1, plus minus 2. And that's it. We only have 4 possible rational roots, which is good. Are all the potential or possible roots. Okay, possible rational roots, very important, rational roots, not complex roots, rational roots. And then what do? We use a synthetic method. It will not be too bad because we only have 4 possible. Very, very important thing about applying synthetic method. You have to write the polynomial in the standard form. The polynomial we have right now is not in the standard form. Degree is 3. If degree is 3, then the standard form is supposed to have 3 plus 1, 4 terms in it, but we only have 3. That means 1 term is missing. Yeah, watch the video from last time. The missing term is x squared. So we're going to rewrite all the 3 terms and also write out the x squared terms. The reason we do not have x squared because the coefficient is 0, but we have to write it out. We need a standard form, very, very important. And then 95x minus 2. Now we have the polynomial in a standard form, and we can apply the synthetic method. Synthetic method. Worst case, we try all the 4 times, right? Worst case, we try all the 4 times. For all the 4 possible roots. So coefficient of x cubed is 1, coefficient of x squared is 0, coefficient of x is 95, coefficient of the constant term is 95, -2. Be very careful. 1, 0, 95, 92. It's a long process and so many details. If you even just mess up one tiny detail, everything's going to be different. We're going to try 1 first. 1, 1, 1, 94, 94, 96. Okay, doesn't work. Yeah, take notes. 1 does not work. And now let's try -1. It doesn't take too much time, right? Just a few seconds. Let's try -1. 1, -1, -1, +1, -4. Did I finish the? Okay, I'm a little bit confused. 94 and +4. This one doesn't work either. Okay, does not work. So take notes. Plus -1 do not work. Yeah, let me do one more time the +1. I don't know if I. So 1, 1, 1. Yeah, I did. It doesn't work. So now we try +2. 1, 2, 2, 4, -1, -2, -4 doesn't work. So +2 does not work. +2 does not work. And we have last one, right? -2. Try -2. 1, -2, -2, +4, -5 plus 4, -1. 1 times -2, +2. There we go. 92 works. 92 is an actual root. Is an actual root. Yeah, we use the rational roots theorem, found 4 possible potential rational roots, and then we use a synthetic method to check each single of them, and then we found out only 92 is an actual root. So very important. Let me mark that. We got an actual root x minus 2, right? That means if we divide f of x by x plus 2, yeah, again, x minus k, your k is 92. So that's why we have x minus -2. Minus -2 is plus 2, equals the quotient. Quotient is going to be here. The quotient is going to be 91, 92x, x squared. So I go backwards. Yeah, do the constant first, and to the left, 92 is going to be degree 1, and then the first one, this one is x squared, 1x squared. So the quotient is x squared minus 2x minus 1. X squared minus 2x minus 1. Okay, that also means we can write f of x as x plus 2 times x squared minus 2x minus 1. And we already got one root. We already got one root, which is 92. And we need to find another 2 roots. How do we find the other 2 roots? We make that quadratic factor is 0 and solve the equation. I'm gonna use a blue. We're gonna make the quadratic factor. Yeah, ideally, if we get lucky, you know, we can factor this quadratic, right? X plus a number, X plus another number, then we can find all the 3 roots. But not every time the quadratic is factorable. And we have to really look at it. So let's see if this one factorable. The quadratic is x squared minus 2x minus 1. I think this one might not be factorable. We make it equal 0, all right? Make it equal 0. We'll do quadratic formula again. A is 1, B is -2, C is -1. Delta B squared minus 4AC, -2 to the power 2. B squared minus 4AC minus 4AC. Okay. Square root of B is 4. -4 times -1 positive 4 equals 8. Yeah, we are right. It's not factorable because you know what? We're gonna have 2 irrational, yeah, 2 irrational roots. We're gonna have a pair of irrational roots because 8 is not a perfect square. Let me double check one more time. 4 minus 4AC, C is -1, so positive 4. Okay, yeah, it is 8. So x equals -b plus minus root delta all over 2a. B is -2. The opposite of -2 is a positive 2. And the plus minus root 8 over 2a. A is 1, 2a is 2. Okay, continue. Root 8 is 2 root 2. Okay, root 8, root 2, root 4. Root 4 is 2. So 2 root 2. All over 2. And you're gonna try the Mickey Mouse again. Left ear, right ear, head. All the 3 parts have common factor 2. That's how do we get rid of the common factor. If the common factor is not shared by all the 3 parts, we cannot get rid of it. In this case, 2 is common, is shared by all the 3 parts, so we can't get rid of it. Left ear, get rid of 2, divided by 2 is 1. Right ear, get rid of 2 is root 2. Denominator, the head divided by 2 is 1, so we don't have denominator. And that's the 2 roots. Okay, that's the 2 roots. Yeah, ideally, you want to write this x plus 2 times x minus 1 plus root 2 times x minus 1 minus root 2. Yeah, but is factoring that in irrational number sets, it takes a little bit effort. So we don't want to do that. I just want to show you those numbers. You make them to take the opposite of them, and you have -2. You have 1 plus root 2. You have -1 minus root 2. Now you have all the 3 roots. We got all the 3 roots. This polynomial doesn't have any non-real complex roots, but it does have 2 irrational roots. Is that clear, everybody? It takes practice. You're gonna have to really practice enough number of problems in order to be good at solving this type of problem. You have to see different varieties. And the process is similar, but you need to also be flexible because every polynomial is different. This problem, degree 3. So we know we are going to have 3 roots. Since the factorization is not convenient, we don't do factorization, so we tried rational roots theorem. Rational roots theorem. We found 4 potential rational roots, and then we applied the synthetic method, found 1 actual root, which is -2. And then we can write a function as polynomial function as x plus 2 times a quadratic factor. And for the quadratic factor, we can always use the quadratic formula to find the other two roots. Together, we have 3 roots. Okay, so this one, let's see. Given the polynomial function, and that 5i is a 0, okay? Wow, this one has degree 5. The task is the same, okay? The task is the same. Find all the roots in a complex number set. Since this polynomial has degree 5, we need to find all the 5 roots. You know, good thing is the question already told us 2 of them. Yeah, it tells us 1. 5i is a 0. 5i is a root. If 5i is a root, then negative 5i, which is a conjugate of 5i, is also a root. Remember that? If a polynomial function has a non-real complex root, then the conjugate of that complex number is also a root. So the question tells us 5i is a root. That means 5i and negative 5i, they are both roots, right? Okay, so that's good. That means since 5i, negative 5i are roots, P of x has factors x minus 5i and x plus 5i. Okay? Yeah, since they are roots, that means the polynomial function has 2 factors. One is x minus the first rule, the other is x minus the second rule. So that is x minus 5i and x plus 5i. And I want to know what is that. I want to know what is that. So we're gonna do for you, or we can do the box method, or we can just use the formula a plus b times a minus b equals a squared minus b squared, right? Yeah, whatever the method you prefer. I'm gonna use the box method to quickly get it done. X minus 5i, x plus 5i, x times x, x squared, 5xi, negative 5xi, negative 5 times 5, negative 25i squared, and those two cancel each other because they're opposites. And negative 25 I squared is negative 1. Negative 25 I squared. Negative 25 I squared is negative 1. So negative 25 times negative 1 is positive 25. So this term is 25. So it's x squared plus 25. You see that? That means what? That means x squared plus 25 is a factor of P of x, okay? And that means we can divide P of x by x squared plus 25 to find the quotient. So what happened is, now P of x can be factored as x squared plus 25 because we already found one factor, right? And then we're gonna have another one, the one in the parentheses, that one gonna have degree 3. We need to find that one, the pink one. In order to find the pink one, we're gonna use long division. We have to use long division because synthetic method only applies when the degree is 1, or when the divisor has degree 1, right? Okay, we're gonna use long division. It's gonna take a little bit. We're gonna use long division. We're gonna divide P of x by x squared plus 25. So P of x is the dividend, x squared plus 25 is the divisor. Very important, use long division. We also require both dividend and divisor in the standard form. Look at the P of X. 5, 4, 3, 2, 1, 0. Okay, that's fine. P of X is the standard form. However, the divisor is not yet. Okay, let me write it down. Dividend is P of X equals 3x to the 5 minus 4x to the 4th plus 58x cubed minus 94x squared minus 425x plus 150. Minus 4x fourth. Double check, triple check. Okay. And the divisor is x squared plus 25, which is not in the standard form. We have to rewrite it. X squared plus 0x plus 25. And now let's do the long division. Very lengthy, right? I know that. Very lengthy. 3x fifths minus 4x fourths plus 58x cubed minus 94x squared minus 425x plus 150. And the divisor x squared plus 0x plus 25. I'm going to do go through the process of long division a little bit fast, all right? Otherwise it's gonna take at least 15 minutes. So use the leading coefficient of the dividend to over leading coefficient of divisor. The quotient is 3x cubed. Put the 3x cubed right here. And then multiply the 3x cubed by the divisor, x squared plus 0x plus 25. And we have 3x fifth plus 0x fourth plus 3 times 25, 75, x cubed. And place that right below the dividend, 0x fourth, 75x cubed. And then subtract. So this cancel, 94x fourth, and then this is going to be negative 17. Let me double check. This is going to be negative 15 times minus 8 is 7, 6 minus 5 is 1. Yeah, cubed, x cubed. And then bring down negative 94x cubed, x squared, and then start another round. Use the leading coefficient of the bottom polynomial, which is 94x fourth, over the leading term of the divisor, is 94x squared. 94x squared is right here. And then multiply 94x squared by the divisor, x squared plus 0x plus 25. And we have 94x fourth plus 0x cubed and minus 100x squared. And put the under 94x fourth plus 0x cubed minus 100x squared, and then subtract, cancel that first term, negative 17x cubed, and this one is going to be 6x squared. Double check 94, 94 plus 100, 6x squared. Okay, let's continue. I hope you guys are with me. Use negative 17x cubed to over x squared. The quotient is negative 17x, and then multiply negative 17x by the divisor, x squared plus 0x plus 25. And we have negative 17x cubed plus 0x minus, let's see, what is the 17 times 25? 425. Negative 425x. So negative 17x cubed. Oh, okay, we have to bring this down. is negative 425x. Yeah, bring that down. Bring this down. Okay. And we have negative 17x cubed plus 0x squared minus 425x. And subtract, and we have 6x squared. Here's a 0x. And then bring down again this one, 150. And then do it again. Multiple rounds. Divide 6x squared over by x squared, which is 6. So 6 here. 6 times divisor. 6x squared plus 0x plus 25 times 6, 150. Yeah. And we have 6x squared plus 0x plus 150. As you can see, the same, right? So done. Remainder 0. The remainder has to be 0, by the way, because x squared plus 25 is a factor. So we finally found our pink. This is the pink. This is the pink, all right? And that pink one should have three roots. And we're gonna have to find the 3 roots for that pink one. Yeah, gonna take a little bit of time. Let's do that. See how many minutes do we have? It's very time consuming. Is this problem required? What's the requirement? Okay, so we're gonna have to do the P over Q. The numerator is going to be the factor of 6, 1, 2, 3, 6. The denominator is going to be the factor of 3, which is 1, 3. So the possible real roots, actual roots, possible rational roots are plus minus 1, plus minus 1/3, plus minus 2, plus minus 2/3, plus minus 3, plus minus 1. We already have that. So don't have this part. Plus minus 6 and plus minus 2. We already have that. So let me double check. Plus minus 1, plus minus 1/3, plus minus 2, plus minus 2 over 3. Plus minus 3 over 1, plus minus 3 over 3, which is 1. We already have that. Plus minus 6 over 1, plus minus 6 over 3, which is 2. We already have it. Okay, so it's gonna take a while to do the synthetic, but let's do it. I need to see this. I'll do here. 3, negative 4, negative 17, 6. 3, negative 4, negative 17, 6. Try 1, 3, negative 1, negative 18. Doesn't work, as you can see. So 1 does not work. Take notes. Try negative 1. 3, and negative 3, negative 7, positive 7, negative 10. Positive doesn't work. Plus or minus 1 does not work. Let's try plus minus 2. Let's try 2. 3, 6, negative 2, negative 4, negative 21. You can tell it does not work. So 2 does not work. Try negative 2. 3, -6, -10, +20, 3. Oh, finally. Here we go. 20 minus 17 is 3. 92 times 3 is 96. 0. There we go. We found one. 92. 92 is an actual 0. Okay. 92 is an actual 0. So the quotient is going to be 3x squared minus 10x plus 3 here, right? That's the quotient. And you know what? I think we can factor that. We can factor that. It's going to be 9 minus. It's going to be, we can factor this as x minus 3 times 3x minus 1. Let me double check. 3x squared plus 3, -9x, -1x, -10x. Yeah, very good. So what happened is we found all the three roots for the pink polynomial. And we can write that pink polynomial as x minus 2 plus 2, because minus k is minus 92, which is plus 2, right? And then x minus 3, and then 3x minus 1. With the other two roots, 5i and -5i, we got all the 5. I'm going to highlight those numbers in red. -5i is plus 5i. This is plus 2. This is minus 3. Oh, this one actually we would have to do a little bit of work. It's actually 1/3. All right, this actually is 1/3. Because if we make 3x minus 1 equals 0, 3x equals 1, x equals 1/3. Yeah, positive 1/3. So as you can see, we have 5 roots. Positive 5i, -5i, 92, 3, 1/3. 1, 2, 3, 4, 5. Done. Very time consuming. Wow, but I think it's pretty interesting. We used both long division and synthetic. I believe everybody loves synthetic but hate long division. But sometimes you have to do long division if the divisor is not a linear. We run out of time. We have something left over. We might consider to cover a couple of them next class. Right? We have some. Let's see. We can cover, yeah, number 15. We can cover a couple quickly next time. But today, we covered a very important and challenging topic: how to find all the roots for a polynomial function in a complex number set. All right, guys, if you have any questions, feel free to reach out. I recorded the class. You can also rewatch the recording. I'll see you on Thursday.
Thank you. See you Thursday.
You're welcome. See ya. Bye-bye.
Miss Gill,
Yeah, Max?
I have a question about the midterm practice.
Yeah.
I didn't know it was timed, and I did like one question and went to sleep, and when I woke up, it was submitted.
Oh,
Do you think there's a way I could like reopen that? So
is it past due?
No, it says it's due on the 28th.
Okay. So could you show me an email? I'll look at it this afternoon when I'm in my office.
Okay.
Can I do that?
Yes, ma'am. Thank you.
Yeah, no problem. Should not be a problem.
Okay.
All right.
Have a good
Let's
one. I'll see you Thursday.
Yeah, you too. See you on Thursday.